Swayam Prabha. Digital India. Educated India.
Okay, so we will continue with the discussion on radiative surface properties. So we have already seen 2 or 3 very important properties, namely emissivity and absorptivity. So we will have to see reflectivity, and then when you extend this properties to surfaces which are not opaque, that is surfaces which allow radiation to pass through, then for example glass, okay, or the atmosphere and so on, we have to consider a very important property called transmissivity, right. So first we will look at reflectivity. As the name suggests, and also from a past experience where we have already worked out problems with reflectivity given alpha, right. We assumed an opaque surface and then alpha plus rho equal to 1, therefore rho is equal to 1 minus alpha. So if I give you the distribution of alpha lambda, you can get rho lambda, you have calculated rho, that is reflectivity and so on. But reflectivity is much more difficult than you thought. It is much more difficult and much more conceptually involved than you ever imagined, because the radiation is coming onto a surface, right. This radiation coming onto a surface can be from one particular direction, or this radiation coming onto a surface could be from the hemisphere above the surface, correct. By the same token, you can look at the reflected radiation going out in a particular direction, or the reflected direction going out in the hemispherical space above this surface. Spectral is another story. Spectral story remains as far as direction is concerned. So you can have radiation incident from a particular direction, you can find out how much is going out in a particular direction, or you can look at radiation which is coming from a particular direction and what is going out in the hemispherical space, or you can look at radiation impinging from a hemispherical space above it and going out in a particular direction, or finally radiation impinging from a hemispherical space above it and it reflecting in the hemispherical space above it. To all this you add the spectral dependence. Okay. So reflectivity is a very dangerous property, okay. If you have to give, so if you have to get really to the bottom of it, it is going to take a long time. So I will just define the basic bidirectional reflectivity, and then we will proceed to those reflectivities which are of engineering significance. But reflectivity is a highly involved property, okay. So let us draw a picture and then things will become clear. Let us take the spherical coordinate system. Alok, did you use the lift or? Huh? Okay. What are all these? Okay, please look at the figure. So this is our spherical coordinate system. The incident radiation I lambda I is a function of lambda, theta I and phi I. So can you tell me theta I from this figure? What is theta I? Which is theta I? This one? Correct? Now this fellow is going out, di lambda r. So this should be a function of lambda, the temperature of that surface, theta r and phi r. It should also be a function of theta I phi I, right? Because from theta I phi I only it is coming. Okay, so please watch the please watch the orange chalk. Yeah, what is that angle? Orange chalk. No, I am looking at the projection. Suppose you shine light, the shadow falls on this. This is this xy plane. So what is that angle? Huh? Phi what?
Phi r.
Phi? Very good, correct, phi r. Is everybody through with this? That is the azimuthal angle. What is the azimuthal angle? This one. The theta is this angle. Okay. Now can you draw phi I? Okay. So I should take a. We'll use the green chalk. No, I think I have not completed it properly. It should be from here, right? Okay. Now, what about this? I have drawn the other normal here. Now, what about this theta phi I? Phi I. Is this okay? Is that phi I or? Correct? From here, we are always measuring from here. Okay, so this projection is falling here. So this is phi I. So I lambda I is incident from a particular angle theta I phi I. The reflected can take place in any direction. We are looking at reflection from an angle theta r phi r. Now please note, as opposed to the absorptivity, there is a significant departure here, because the reflected I am putting it as di lambda, because this theta r phi r is a small direction. There is a small solid angle in this big 360 degrees over the hemisphere. Therefore I expect the reflected component to be small as opposed to the incident. Therefore I call it as a di lambda r. Is it okay? Now I have to define the bidirectional spectral reflectivity. Okay, this is the what is this bidirectional spectral reflectivity? Directional spectral reflectivity. Incoming is from theta I phi I, outgoing is theta r phi r. It is still spectral, so it is directional. Therefore it should be rho lambda dash rho lambda dash. Yes. No, I lambda I is a finite radiation which is coming in. But since we are not considering whatever is going out in the full hemisphere in a particular direction, I expect that to be a very small quantity as opposed to I lambda I. Therefore I call it di lambda r. Correct? Because it can go equally in all the directions, unless it is a very specular surface or something. Okay, consistent with my understanding that if it is a diffuse surface or whatever, if it is a surface which can reflect in all the directions, what is coming out in a particular direction will be much smaller compared to this. Okay, therefore I call it di. Is that clear to everybody? Now therefore I define this rho lambda I will remove this fellow. So it will be a function of lambda Ta will be equal to di lambda r. Divided by please note that the denominator I am taking the cos theta because projected area, I am also multiplying by d omega I, which is the elemental solid angle, subtended in the reflected direction theta r phi r. If you do not like this, if I do not do this, this rho lambda double dash may be 0.00001 something like that. Okay. So I am multiplying I lambda I by a small angle cos theta to ensure that rho lambda double dash is decent. Please note that this bidirectional spectral reflectivity is not a dimensionless quantity. Huh? No, allow me to complete. The bidirectional reflectivity by definition is not a dimensionless quantity. It has the units of steradian to the power of -1. Okay. So the bidirectional reflectivity is not dimensionless, it has a units of steradian to the power of -1. But you can see that the bidirectional reflectivity is conceptually very clear, and if you have got a good lab, if you have good laboratory facility, it can be experimentally measured, correct. But in engineering we are more interested in, finally we are interested in rho, okay, or at the most we are interested in rho lambda, but this rho lambda double dash and all that, mostly only physics people are interested. It is coming in one direction, it is going another direction. Most of our surfaces are diffuse, that means it is reflecting diffusely in all the directions, or sometimes we use specular surfaces, that is for special applications. Otherwise from one angle it is going to the other angle and all that is not a fundamental concern to engineers, but it is important that all other reflectivities have their origin from this rho lambda double dash. So this is the basic. So it can be calculated, it can be experimentally measured, it can also come from theory of optics. So if you are strong in optics, then this rho lambda double dash, you can get this rho lambda double dash. Once from this rho lambda double dash you can calculate rho lambda dash, rho lambda and so on and proceed. Are you getting the point? So it has limited engineering significance, but it has got lot of conceptual importance. Okay. So it is so the first time we have a property which is not dimensionless, which has got steradian to the power of -1, which means that we have to use it with caution in problems. In this course we will not work with rho lambda double dash hereafter, but I do not want this is a graduate level course, I do not want you to go out of this course without knowing that there is something called rho lambda double dash. I can just start with rho lambda and then how to convert rho lambda to rho, I could have just finished the whole thing in 5 minutes, but you should know that there is something called the bidirectional spectral reflectivity. Okay. Now if I have a conceptual depiction of reflectivity, so reflectivity can be you can talk about a directional, correct, or you can talk about a spectral, very good. Under directional you can talk about a directional reflectivity. That is the which we saw. It is actually bidirectional spectral reflectivity, but it is usually called BDRF in capitals, that is bidirectional reflectivity. This is what the optics people, physics people will call. So it is a direction to direction from theta I phi I to theta r phi r. I can have a directional to hemispherical, correct, from a particular theta I phi I into the hemisphere above it, okay. I can have a hemispherical to a directional. Then finally I can have a hemispherical to hemispherical, that is of engineering importance for us, okay. This is called bihemispherical. Then I can integrate with respect to lambda, so I can get bihemispherical total reflectivity. So the bihemispherical total reflectivity involves how many integrations? 5. Integration with respect to theta I, integration with respect to phi I, integration with respect to theta r, integration with respect to phi r, integration with respect to lambda. So finally rho, you are simply writing that rho came after doing 5 integrations, is that okay. So this is simply rho lambda, correct, this is simply rho lambda, double dash is gone, okay. So this is basically rho dash. Then if you integrate, you will get, if you integrate both, you will get the hemispherical, bihemispherical total reflectivity. Now we will go to bihemispherical spectral reflectivity and then total reflectivity, or you can keep this bi silent also. When somebody says hemispherical spectral reflectivity, that hemisphere is applicable for incident as well as reflected direction. Yeah. So what will be the symbol for this? Rho lambda, very good. Rho lambda is expected to be a function of lambda and then temperature of the absorbing surface, okay. I lambda r, I lambda reflected, okay, should be a function of lambda T A, yeah, all, okay. Lambda if you want you can put theta I phi also here, okay. So cos theta I So that I lambda reflected in the numerator, okay, that I lambda reflected can be written in terms of I lambda I multiplied by rho lambda dash, where rho lambda dash can be directional to hemispherical or hemispherical to directional, okay, and that rho lambda dash can be connected to rho lambda double dash, which is directional to directional. To cut a long story short, if you know the bidirectional reflectivity rho lambda double dash, it is possible for you to accomplish the integration and calculate the numerator, right. If you know the directional distribution of the incident radiation I lambda I, you can calculate the denominator. With this we can straight away get the rho lambda, okay. So if alpha lambda information is not available to you, and if rho lambda double dash information, that is bidirectional reflectivity, is given to you, you can calculate rho lambda, and if it is opaque surface, 1 minus rho lambda can be taken to be alpha lambda. So from alpha you can go to rho, from rho you can go to alpha, and all those manipulations you can do. But however, the things get little complicated if I suddenly say that tau is not 0, it is not opaque, okay. From there is only one more reflectivity which is involved, which is basically the hemispherical total reflectivity. Let us do one more and then I will work out the quiz paper. And before that you want to write the directional total reflectivity, or we will get rid of that? You do not want that, okay. Let us go to this straight away. So rho is equal to there may be I lambda I into cos theta, that cos theta may come in the numerator and denominator. Since cos theta and d lambda are not related, the cos theta can be pulled out in the numerator and denominator, we can remove it, okay. So before that there is one thing, right. I leave it as an exercise for you to get the total reflectivity, okay, that is directional total reflectivity. What did I put? Why did I put rho dash? I should have rho double dash, no.
Hemispherical with respect to
so this is a I did not want to go deep into this because by the time the class is over you will all get confused. I can have a directional total reflectivity, I can have a directional directional or hemispherical directional, correct. So that is why I can have rho double dash, rho dash and all that. Then you may have an issue with whether from a direction to hemisphere or hemisphere to direction, what is the relationship, and okay, so it gets messy, okay. So that is as far as the total reflected is concerned. Now this is very simple, if you know rho lambda you can get the rho, okay, but if you don't know if you don't know I lambda I, suppose I do not give you the distribution but I say that the incident radiation is from a black body at 5800 Kelvin, then you can convert it into EB lambda d lambda and use the F function charge and use the alpha lambda and take 1 minus alpha lambda as rho lambda and calculate rho, is that okay. Or if I give you rho lambda double dash, then you can do all the integrations and get up to rho lambda and then calculate rho, then if it is opaque surface alpha is 1 minus rho. Or if I give a problem in which I give you rho lambda as well as tau lambda, then alpha plus rho plus tau is equal to 1, you can calculate alpha, is that okay. So you should seamlessly go from one property to another property, okay. So this is as far as reflectivity is concerned. Now what is the story for a surface which is not opaque, which allows some radiation to pass through? Such a surface, so what happens? Such a surface is called a participating medium. Glass is an example, lenses, filters, atmosphere, then combustion chamber filled with gases. Okay, in all these cases there you cannot assume that the medium is opaque. So there is a transmissivity involved, therefore you cannot simply put alpha plus rho equal to 1. So alpha plus rho plus tau is equal to 1, therefore you have to do the same story, spectral transmissivity, total transmissivity, hemispherical total transmissivity. We will quickly go through those derivations and then we will see, then we will work out some problems on, I told you, tinted glass, sun control film, if you put a tinted glass, whether it really helps in reducing the incoming radiation, I mean the radiation which is transmitted. Okay. So I will stop here and I will we will quickly see the solution to the quiz paper. So first you want to have the papers and then, okay, you can take a break for 3 minutes, I will distribute the paper and then okay. Okay, the first problem is assuming the temperature, determination of the temperature of the earth, right. So this problem is not fully correct because there is an albedo associated with the earth. The earth has a reflectivity, the earth is not a black body, okay, there is a reflectivity associated with the earth, therefore the temperature you are calculating will be different from the actual temperature which is the mean temperature of the earth, but that is okay. For starters you can assume it is black. And so the first problem is basically a test of whether you know your solid angle and solid geometry well, okay. So it is very simple. Okay, so this is the earth and this is the, so this is the earth and this is the sun. So the distance is 1.5 into 10 to the power of 11 meters. Okay, so dE okay, and the diameter of the sun is so the sun has an equivalent temperature of 5800 Kelvin. So we first assume the sun to be a black body, therefore basically the emissive power of the sun is given by sigma T to the power of 4, so basically okay. Now the intensity associated with the solar radiation is E to ES divided by pi, okay, which is 20.42. Some people have done it very correctly, I do not know whether you anticipated, and maybe you looked at the old question paper or 4 years back I gave this question, I do not know, but basically these sorts of questions I cannot change any data, right, I cannot change the diameter of the earth or the diameter of the, so some questions have to get repeated. I see to it that we do not repeat, but this question we cannot change anything, okay. So from next time onwards I should ask you to calculate the equivalent temperature of Venus, Mars, no? Huh? Of course Pluto is out of the solar system right now, yeah, bye bye, Pluto is not there, it is supposed to be part of something else, okay. Now I is there, now just calculate the solid angle and find out what is the radiation which is incident, what is the power which is coming on to the earth, okay. Under equilibrium whatever is going out must be equal to whatever is coming, earth is black, therefore sigma TE to the power of 4 of the earth must be equal to whatever is incident, therefore TE equal to Q divided by sigma whole to the power of 1/4, that is the story, right. Now the solid angle What is the dA? Area of the receiving surface. Who is receiving? Earth. Okay, so pi d squared by 4, that is the projected area. The beauty of this problem is, even if it is a sphere, what it receives from the sun depends on the pi r squared or the pi d squared by 4, but when it emits, it will emit from 4 pi r squared. That is why some people fail to recognize this 4, they got orbit temperature like 557 Kelvin, 450 Kelvin, 557 Kelvin and so on. Okay, the earth is the projected area of, as far as incoming is concerned, is pi r squared, but when it is emitting, it is 4 pi r squared. Okay, so pi d squared by 4 cos 0 divided by, this is very small, 5.81 10 to the power of minus 9 steradian. Okay, this is d omega. Q earth is equal to I sun okay. Okay, please look at the board. I am spending a lot of time on this because other problems all of you have done, most of you have done the other problem. I sun we know, we just calculated area of the sun. What is area of the sun?